So what we have to discuss today is right here, PID controllers. PID controllers, very commonly used actually in most of the control systems. They employ PID controllers to reduce the value of the gain between the input and the output. And PID controller, they employ three different paths. One path is the proportional path, one path is the integral path, and one path is the derivative path, and that's why they're called PID, proportional, integral, and derivative. The controller gain, as you can see, is of a type Kp plus K1s plus Kds. Kp is the proportional. K1s, remember this is the S domain, so this is the Laplace domain. So K1s correspond to the integral of K1 whatever dt, whatever is that, and then as a function of S, whatever is that, and then Kds represent your differential dt. Kd is a function ut, let's say, whatever is that. So this is going to be ut here as well. When you take the integral in Laplace domain, it's going to become 1 over S, or and then when you take the differential, it's going to become S. Whatever the system, I'll just write down xt dt and xt, whatever xt is going to be. So right here, actually, it's shown right here. If your Kp represent the proportional, Ki represent the integral gain, and Kd represent the derivative gain. 7.4 right here. You can see that is your controller with three paths: proportional path, integral path, and differential path. Your error function is going into each one of them. Proportional path is taking that error function, multiplying it proportionally by a gain. Integral path is taking the integral of the error function, and then differential path is taking the differential of the error function, and then all three outputs of all three of them are going to be added together, and that is going to go into your process, GS. Now, sometime one is present, sometime two of them are present, sometime all three. Differential path is very rare, though. You will see why. Many times proportional path is present, integral path is present, differential path is not present. And sometimes differential path is present, integral is not present. But differential sometimes poses an error because it can generate a very high noise in the control system for small changes. So this is the error function, and this is basically the output of this summation u of t, which is represented by Kp error function plus Ki integral of the error function and Kd differential of the error function. The whole idea is how to set the gain of each path, Kp, Ki, and Kd, in order to optimize the controller gain and control the process in order to reduce the amount of the error that is right over here. That's the whole idea of using the PID controller. So it gives better performance over a simple feedback controller by determining how much or how fast corrective action can be applied to a process by using varying amounts of proportional, integral, and derivative action. So how much is going to be supplied and how fast you have to change it. Both information, they are important in a practical control system. All right, let's look at each one of them. First of all, proportional creates an output, of course, which is proportional to the magnitude of the error signal. So as you can see in this diagram, you have the error signal in blue, and then the proportional, whatever the value of Kp was multiplied by this signal. So the only thing that is going to be changed is going to be the magnitude, but the shape of the error signal is not going to change and it's going to be the same shape. In the time domain, you will have, after it settles down, you will have your steady state value and your output. They will have some offset or some error between the two of them with the proportional path. And that error depends upon how much gain you are supplying for the proportional path. So for proportional gain, the closer we get to the desired output input value, also called the set point, so this is the set point, the less it will push the actual output. Eventually, the process just runs continuously close to the set point, but not quite there. So it is running close to the set point, which is this line, but there is still some error. For the integral, creates an output proportional to the duration and magnitude of the error signal. As we know, the integration is summation of the area under curve, and that's what it is doing. This is your curve error signal, and it is taking the area under the curve and producing the output for the integral block. The larger the area, as you can see, the teal one is larger the area, you're gonna increase the value of the integral block more, and the smaller the area, you're gonna have less steep curve, which less height. In the time domain, I uses past information to generate a signal to control the process. The longer the error and the greater the amount, the larger the integral output, as shown in 7.6a. As long as the error exists, integral action will continue. When the error is eliminated, the integral term will cease to grow. Proportional and integral block together will push the actual output closer to the set point, as you can see over here. So now you're adding the proportional output and the integral output, and your time domain output is going close to the set point value. And the third one is the derivative block. Derivative block creates an output signal proportional to the rate of change error signal. The faster the error changes, the larger the derivative output is going to be. This is the best estimate of the future trend. So proportional is the present, integral is the past, and differential is the estimate of the future trend of the error signal. Based on its current rate of change is called anticipatory signal as well. Control is not very commonly used in controlling process as it is very sensitive to the measurement noise. It is used in motion, sometimes it is used in motion control application. Most of the PID controller, they work perfectly fine with the proportional and integral gains. Many times you don't really need the derivative gain. I found this video, which is a really good video, and not sure why it is not. This is an embedded YouTube video. Let's see. This describes it. PID controller. Right.
Let's talk about PID control. Chances are you've interacted with something that uses a form of this control law even if you weren't aware of it. And so it's worth learning a bit more about what this control law is actually doing and how it helps us. However, often when we're learning something new in control theory, it's easy to get bogged down in the detailed mathematics of the problem. So in this video, we're going to skip most of the math and instead focus on building a good intuitive foundation. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. We start with a plant. This is what we call the system that we want to control, or the system whose behavior we want to affect. The input into the plant is the actuating signal, and the output is the controlled variable. Different industries refer to these signals by various names, so you might hear them called something else, like plant input and plant output. But regardless of the names, the basic idea of a control system is to figure out how to generate the appropriate actuating signal, the input, so that our system will produce the desired controlled variable, the output. And that's basically the job of the control engineer: produce the right input into the system to get the output that you want. And just like before, the output you want also goes by various names. Here I call it the command, or the commanded variable, but you might also hear it as the set point, the reference, or the desired value. And in feedback control, the output of the system is fed back, hence the name, and compared to the command to see how far off the system is from where we want it to be. This difference between the two is the error term. If the output was exactly what we commanded it to be, then the error would go to 0, and that is what we want, 0 error. So the question is, how do we take this error term and convert it into suitable actuator commands so that over time the error is driven to 0? And the answer is with a controller. Let's illustrate this with an example. Imagine you are standing on the goal line of a soccer field and you want to walk to the half field line 50 meters away. In this case, you are the plant. The actuating signal is the speed and the direction that you walk, and your current location on the field is the output variable, or 0 meters to start, and then 50 meters is the command. Therefore, at the beginning, your position error is 50 meters, or 50 minus 0. You still have a ways to go. Your brain, being the controller, tells your legs how fast to walk. And one way your brain can do this is to use the error at the present moment to decide your walking speed. Here I've set our controller to the value of 0.1. This means that if we take the error in our system and multiply it by 0.1, we'll get our walking speed. So if our error is 50 meters like it is at the beginning, then we'll start off walking at 5 meters per second. With a proportional controller like this, we start reducing the error quickly since we're far away, and then gradually slow down as we get closer and closer to our goal. In this way, we would eventually and asymptotically reach the half field line, at which time the error would be 0, and our proportional controller would multiply that by 0.1, which would generate a walking speed of 0, stopping us right where we want to be. If we wanted to adjust the amount of time it took us to get to the goal, we could increase or decrease the multiplier term. Regardless of the gain value chosen, this type of controller will eventually cause us to stop right on the goal line. So this proportional controller seems great. I mean, just multiplying the present error by a number seems to work. Well, let's try it again on a different system and see if it performs the same way. In this second example, you want to design an altitude controller for a quadcopter drone. The drone has 4 propellers, and when they all spin up together, they produce a force that lifts the drone up into the air. This is similar to our walking example in that we're trying to get to a specific location, but this time we want to get our system to hover at an altitude of 50 meters. Our plant is the drone, and the output of this system is altitude. Now the input of the system is not walking speed, but propeller speed. And all in all, it seems like a pretty similar problem. So how well does a proportional controller work in this case? Well, when the drone is on the ground, there's an error of 50 meters, which would generate a large propeller speed, causing the drone to lift off and start to rise, reducing the error. So far, so good. But let's imagine the drone was able to rise all the way to 50 meters. What would happen now? Well, the error would drop to 0 since the command and the output are both 50 meters. This would then shut off the propellers, lift would stop, and the drone would fall back to Earth. Now when that happens, the propeller speed would start to increase again as the error grew. There is a certain propeller speed where the lifting force is exactly equal to the weight of the drone, and at that speed, the drone will hover. So where would our proportional controller hover this drone? Well, that depends on the controller gain. Now let's assume for the moment that the propellers need to spin at 100 RPM in order for the drone to hover. If our proportional gain was 2, then the drone would hover right at ground level, since an error of 50 times 2 is 100 RPM. However, if we increased the gain to 5, the drone would rise at first, but then stop at 30 meters, since the error at that point would be 20 meters, and 20 times 5 is 100 RPM. A gain of 10 would produce an error of 10 meters, and a gain of 100 would produce an error of 1 meter. And no matter how high we increase the gain, the error won't go away. It'll just get smaller and smaller with this system and a proportional controller. So we can see that a simple proportional controller doesn't work in every situation. It works with our walking example, but for our drone it created this constant error. This error is also called steady state error. So, how can we tweak our controller to get rid of this steady state error? We can do that by letting our controller use past information, or specifically adding an integrator path in our controller that's added alongside the proportional path. An integrator sums up the input signal over time, keeping a running total. Therefore, it has this memory of what has happened before. Basically, it's keeping track of the past. Now, if the drone gets to steady state below the desired altitude, the error term is non-zero. And when a non-zero value is integrated, the output will increase. Now, as long as there's error in our system, the integral output will continue to change. And this increased value from the integrator path will increase the speed of the propellers, and the drone will continue to rise. These two paths, the proportional and the integral path, work with each other to drive the error down to zero. And with this controller, when the drone is hovering at the desired altitude of 50 meters, the proportional path is doing nothing, since the error is zero. But the integral path has been summing and subtracting values until it came to rest at 100 RPM. Remember, this is what we said was needed for the drone to hover. And that output from our integrator will not change, since the input to the integrator at this point is zero. Alright, this proportional integral controller is it. This is what we want, right? Something that understands the present and has memory of the past. Well, looking at the past and present error will get us to our goal in this situation. However, the path the drone takes to get there might not be ideal. Imagine this situation. Right before we get to 50 meters, there's an interesting situation that can occur. The proportional path is basically zero, since at this point the error is so small. But depending on how the drone got to this height, the integrator may have summed to a value over 100 RPM. This would cause the drone to keep rising, which is what we want since we're below the 50 meters. However, to remove that excess propeller speed, the drone will have to go higher than our goal to create a negative error. This negative error, when summed, lowers the output of the integrator and slows the propellers down. This overshooting of the goal might not be desired. Luckily, there is a simple way around this problem, and that is by adding a path to our controller that can predict the future and respond to how fast we're closing in on our goal, and we do that with a derivative. A derivative produces a measure of the rate of change of the error. That is, how fast the error is growing or shrinking. For example, if our drone is rising quickly and fast approaching our goal, this means that the error is quickly decreasing. That decreasing error has a negative rate of change, which will produce a negative value through our derivative path. That negative value will be added to our controller's output, therefore lowering the propeller speed. Basically, our controller is using changing error to determine that we are closing in on our goal way too fast, and then prematurely slowing down the propeller speed, preventing the drone from overshooting. And just like that, we've created a PID controller, proportional, integral, derivative. This is a versatile controller that uses the present error, the past error, and a prediction of the future error to calculate the appropriate actuator commands. These three branches each contribute some amount to the overall output of the controller, and as the designer, you get to decide how to weigh each contribution. You do this by adjusting the gain term in each branch. This is called tuning the controller. Now, if your controller contains all three branches, it's called a PID controller. Now, if the gain of one or more branch is set to 0, taking it out of the equation, then we typically refer to that controller with the letters of the remaining paths. For example, a PI or a P controller. PID is just one form of a feedback controller, but they're pretty easy to understand and implement. They are the simplest controller you can have that uses the past, present, and future error, and it's these primary features that are needed to satisfy most control problems. Not all, but a lot of them. That's why PID is the most prevalent form of feedback control for a wide range of real physical applications. Now, there's a lot more to learn on this topic, and if you stick with this series, we're going to explore PID controllers in more detail. Now that we have a general understanding of what PID control is, we'll move on to how we implement one, how we tune it to do what we want, and we'll watch it in action on some real hardware. So if you don't want to miss these future Tech Talk videos, don't forget to...
All right, so this, and again, there's a whole series, so you can watch the series. It's pretty interesting. So that's what the PID controller is in a nutshell, without going into much of the math that is there. But it's a very commonly used controller. Many students actually employ that in the senior design as well. I remember recently someone was using PID controller in the senior design to reduce the gain of was a robot or a moving vehicle or something, and they use PID controller in Python, if I remember correctly. It's already a function, of course, in MATLAB and Python. All right, moving on. If we set the derivative gain KD to be equal to 0, we have a PI, proportional plus integral controller, and the transfer function of that is going to be Kp plus Ki over S. If we do the integral to be 0, it's going to be Kp plus Kts. A PID controller can also be viewed as the series combination of Pi plus PD controller, proportional integral and proportional derivative controller. If you cascade them, you can also get a PID control. If you write down the transfer function of Pi PD controller with their own gain variable as shown in by 7.17 and 7.18 on the next page, then we can cascade them to get the gain of a PID controller. So this is a PI controller, Kp plus K1S, just showing a tilde over here to differentiate that the gain is from a PI controller or from a PD controller. We are showing a bar on top of the gain. If we cascade them, that is, if we multiply the gains together, they're in cascade, then we can multiply these two together, and the end term is going to be one constant, which is going to be comprised of these terms, and then one term with the differential, and then one term with the integral. So just to emphasize that, if you cascade a PI and PD controller, then you can get a PID controller. So you can develop them separately, add them together, and have a PID controller. From the PID controller function given in 713 and 719, 719 of course is this, and 713 is, I don't know where 713 is, right here, 713 right here, this GS. We can write the transfer function of the controller, Kp plus K1S plus KDS, and simplify it, KDS square plus KPS plus Ki over S, and KDS square plus AS plus B over S. That's a generic term that we are using. A is Kp over Kd, and if we take the Kd as a common factor out, then it's going to be S square plus Kp over KdS plus Ki over Kd. So B is Ki over Kd. And that's a quadratic equation, so it will have two zeros, S plus Z1, S plus Z2, and then you have one pole at S is equal to 0. So PID controller will introduce a pole at S is equal to 0 at the origin, and two zeros anywhere in the complex S plane. For a unity feedback control system shown in this figure right here, let the process transfer function be this. So from this, basically, what do you suggest about the stability of a PID controller? What type of stability do they behave? Huh? It's a marginally stable system because you have one pole at s is equal to 0. All right, let's look at the plant or process. Let's say the transfer function is 1 over s plus 2, s plus 3. Let's use PID control with complex root -3 plus minus j1. Therefore, the transfer function of the system will be given by. So GCS is a PID controller, and it has complex root -3 plus j1 and -3 minus j1. So KD s plus 3 minus j1, s plus 3 minus j1 over s. This is the equation right here. This is what we are using. And this is your GS. Characteristic equation from this, it's going to be 1 plus KD s square plus 6s plus 10 and divided by s cube plus 5s square plus 6s. And then we draw the root locus of that. From the root locus plot, this plot 7.9, as you can see, we have 3 poles, and then we have 2 zeros, and of course one of the zeros is going to be sitting at infinity, where this root locus is heading to. These 2 root loci, again, this is the program, that's my program, that's why you see different color graphs. So these 2 root loci, they are heading towards each other, and then at a breakaway point, they break away from the rail axis and then start moving towards their respective zeros. And those zeros are, of course, -3 plus ji and -3 minus ji. From the root locus plot shown in the previous figure, it can be seen that the value of KD, as the value of the KD increases, the complex roots, they approach 0. These complex roots, they approach 0. Of course, you have one of the rail roots as well. In general, any complex conjugate zeros, we can write the transfer function of the system. KD s plus z1, s plus z1, these are the complex conjugate zeros, these 2 right here. 1 plus GS GCS, s plus R2, s plus R1, and s plus R1. So these are 2 complex conjugate. These are 2 complex conjugate poles, and this is the rail pole. So the transfer function corresponding to your PID controller. In this case, you have one rail pole, which will be increasing on the rail axis towards the 0 that is sitting at infinity. And then you have complex conjugate poles that are going to be moving towards the 2 complex conjugate zeros, which are these 2 poles. Now, initially, these 2 poles are also going to be real. They will have the real values, and they will be increasing towards each other. But at some point, of course, they are going to break away from the real axis right here. They're going to break away from the real axis and then start moving towards the complex conjugate zero. The same root locus is shown for generic values in figure 7.10. So this is for specific values for our transfer function that we discussed, and this is for generic values. Observe that the 2 complex poles are moving towards complex zeros, and the third pole, which is real, is moving toward the third zero located at infinity. So it has a very distinct pole zero characteristics, basically, or the root locus characteristic. When KD value is maximum in figure 7.9, KD value is maximum. When it's going to be maximum, it's heading towards, of course, 0. So very close to the 0. when we calculate the value of the KD very close to the 0, which is 10. Complex poles are closer to complex zeros, and their values are negative 3.1 plus minus j 1.3. So here I basically found, I went as close to 0 as possible and found that this value of k right here was approximately, or I used 10 value for k, and it went as close to 0 as possible. If I use higher value, it's going to go even closer to that. Value of the real pole was 8.780. Substituting these values in 7.24, transfer function can be written as this. If we substitute the value of k, which is 10, in 7.24, write this equation. So value of k is 10, s plus z1, s plus z2. We have these two values, z1 and z2, and the three roots. So the three roots are these, complex conjugate root, and this is the real root. So we went ahead and plug in all the values in this equation right here, and the transfer function is going to come out to be this. And then we plotted the unit step response using the step function. And from that, we can find out what is the peak value, steady state value, peak time, overshoot, and all those things. System exhibit desirable characteristic with less overshoot and a small settling time. If shorter settling time is required, system design should include the two complex zeros to be further left in the complex plane, and the value of KD should drive roots near the complex zeros. So all these are design basically characteristics. As if you want the shorter settling time, if you want smaller overshoot, then how are you going to change the value of KD in order to do that? Stable shows the effect of increasing different PID gain values on the step response. If you want to increase the proportional gain, percent overshoot is going to increase, settling time is not going to have any impact, error is going to decrease. If you increase integral gain, percent overshoot is going to increase, settling time will increase as well, and you can go up to 0 steady state error. And if you increase the differential gain, overshoot will decrease, settling time will decrease, and a steady state error will have no impact. So all three of them working together is going to give you the optimum solution for different cases, as we saw in the video as well. Don't have to apply for every control system, but whichever is needed, like the drone, if you apply all three of them, it's going to work better. If you're just walking, the example that shows, you don't really need the differential in that case anyways. PID controller tuning. Of course, tuning means that we are adjusting KP, KI, and KD based upon that should be KD, KP, KI, and KD must be determined. Process of determining these values are called tuning, and there are two very commonly used tuning methods. One is manual tuning, and one is Ziegler-Nicholas tuning. Manual tuning method, values of gain are determined using simulation for a step input with minimal analytic analysis. In some cases, actual testing on the system is done, and gains are decided based on the values that you're collecting from the experimentation. And Ziegler-Nicholas is more analytic and has many variations. We're not discussing at this time these two tunings. The problems that I have, I think I have problem for homework. The problem will be based upon, of course, this type of system, different values of zeros and poles and stuff. So I don't know what problem I had, but of course I'm going to post that problem. So this is just a general introduction of PID controllers and how the root locus of PID controller look like, and what do you do basically exactly in order to reduce the overshoot, in order to reduce the settling time, and all those things. that you can change. Any question that you may have about PID controllers? Of course, we did not cover a lot. It's a very long topic, of course, but I guess we're just gonna do the basic understanding of PID controller and the transfer function and all those things. Not going into tuning right now, basically. That's going to be a very lengthy topic, the tuning topic. All right. Well, if there is no question, then that's all I have for today and from this chapter. As I said, I do have a homework problem based on the PID controller that I'm going to post. I think I have one. I'm going to create one more problem, so at least a couple of problems that I'm going to post, which is similar to what I discussed towards the end about the root locus and the transfer function and the step response and all those things. So work on that problem when I post it, and I will see you guys next week. And if I give you a quiz, it's going to be similar to basically what I'm going to give you in the homework problem.